I hope you can hear me. Can you hear me?
Yes, sir.
Yeah, so we'll start right now. Can you see the screen? Okay. So today we're going to start a new topic, and this is very important for physical chemist. And this is a name. What I'm going to do actually today is I'm going to talk about the structure of liquid. So let us okay, just a minute. So we'll talk about the structure of liquid, which is today's topic. So I'm going to talk about what is known as distribution function theory of liquids. I hope you can hear me.
Yes, sir. Yes, sir.
Okay, so let us go back and recapitulate few things we already know. So let us go back and recapitulate few things we already know. For example, the partition function, the canonical partition function. We have been using this very frequently. So let us write down the partition function. I'm calling it Q, and you know that it is given by this expression. Okay, but whenever I have sum over states, it essentially tells you that we are dealing with quantum system, isn't it? Some quantization is there underlying. So energy is quantized essentially. Energy is quantized. Basically, you are using something like quantum mechanics whenever you have sum. But think of a purely classical system, because many times we actually mix quantum with classical in statistical mechanics. Now, if you have purely classical system, so the system is described by the system is described by Hamiltonian. Okay, so H is the Hamiltonian of the system. Of okay, so formally, okay, actually, uh, this Hamiltonian depends on what? Depends on position and momentum, isn't it? So I can write r to the power of n, comma p to the power of n. Is this clear? My notation of r to the power n means 3n position coordinates. Why I am using r to the power of n? Any idea? Why not 3n? Because in my notation, r has actually each r has three components x, y, z. You understand? Are you there?
Yes, sir. Yes, sir.
Yes, sir.
This is my notation. Just because I'm following some book, and I had earlier used r to the power 3n, but whenever I write r to the power of n, it basically means there are 3n coordinates, but for each r you have three components. So similarly, p to the power of n also means 3n momenta coordinates. This fine. So formally, if I write down the Hamiltonian of the system, it has to be kinetic energy plus potential energy, isn't it? Kinetic energy, I'm writing it as K, capital K. This is my notation. It's a function of what? Can anyone tell me? You must have noticed it is a function of only momentum, isn't it? Yes. This is your kinetic energy. What are the potential energy? V or U, I'm calling it U. You can call it V, doesn't matter. And this depends on only R to the power of n, isn't it? This is the structure I have for the Hamiltonian. Okay. So now if you are asked to write down the classical canonical partition function. So basically canonical partition function for a purely classical system. Hamiltonian is given, no? This is Hamiltonian. This is Hamiltonian, no?
Yes, sir.
So what should I write here? So I'm calling it Q. I can call it Q classical. This has to be, other than summing over states, actually I should integrate over all position and momentum coordinates. Is this clear? That I have to integrate over all position and momentum coordinates.
Yes.
So basically I'll have something like dr to the power of n, dp to the power of n, exponential of minus beta h. Now h is a function of r to the power of n, comma p to the power of n. But is it complete or you have to write something else? It is not the whole thing. If you go and check my notes, you will see that I have to divide this by h to the power of 3n. Okay. And then if I assume this particle is indistinguishable, I should divide by n factorial. If we assume the particles are indistinguishable. So again here I am bringing this indistinguishability. And this is your partition function. So rather than calling it Q classical, I am calling it Q only. Okay, so your Q is this. Any question so far? This is not very difficult. This is the definition. Because it also take care of the dimension, this h to the power of 3n. This is the, you remember, this is the phase volume, no? Del r n into del r pn is, isn't it? Remember this.
Yes, sir.
Essentially,
Yes,
I
sir.
put that here. N factorial because particles we are assuming.
Indistinguishability.
So this is your classical, kind of classical, semi-classical partition function. This is a partition function people use everywhere. Okay, whenever you do classical statistical mechanics. Now, with this classical function, partition function in mind, I can define something like this. For example, I can define a function which is f, which is a function of r to the power of n, comma p to the power of n, and this function I'm calling it is actually, it's a probability distribution. For observing a system. Okay. Observing a system My system is made of n particles. You know this. Okay. At phase point, remember the concept of phase? Remember
Yes, sir.
that if I collect all the momentum coordinates and all the position coordinates and plot the trajectory of the particle to look like this. So any of these points is actually this, isn't it? Of course, we are in equilibrium. So we are dealing with equilibrium. So it has no time dependence. And what it should be, any guess, since you have done good amount of statistical mechanics, you should be able to tell me what is this expression. What should I write on the right hand side? If you know
E power
Boltzmann distribution,
exponential minus beta h r n t n divided by integral.
yes, it has to be like this. So it is
Yes, sir.
it is nothing but your exponential of minus beta h, which is a function of r to the power of n divided by actually the partition function itself. But actually, if you divide partition function, also have to multiply it here with this 1 over n factorial h to the power of 3n. So actually, you different if you divide it by this. Anyone has a problem? Tell me. Huh? This is how it is, isn't it? A reminder: what is this dr to the power of n? This is dr1, dr2, right? Here n particles are there, no? Similarly, dp to the power of n, dp1, dp2, dpn. But don't forget this one, that any dr is actually dx, dy, dz. Similarly, any dp is actually
dpx,
actually,
dpy, dpz.
yeah, dpx, dpy, dpz. So that's why it is 3n plus 3n, 6n dimensional integral. Clear? Not a very difficult thing, huh? I should do one thing actually. It looks very bad. I write the exponential property. Anyway, again, it is not looking good. You understand, no? I'm written. Fine.
Yes, sir.
Now, this one, I can further write it like this. I write this as exponential of minus beta. You remember what is h? H is made of two terms, no? Terms. Remember this? And here also I can do the same thing in the denominator. I hope you can follow this.
Yes, sir.
What is K? K is kinetic energy, no? K is potential energy. Now further I split into two. The product of two I can write. How? Because it is exponential. I can have exponential of minus beta divided by, because these integrals are independent, no? Just look at the structure of the Hamiltonian. Because kinetic energy depends only on the momentum coordinates, isn't it? Momentum coordinates into, okay? This is fine? Any problem you tell me. So I can write this f rn comma pn as the phi, the first part, capital P. Huh? So what is phi? You understand what is phi?
Momentum space distribution function.
Yeah, this one I am calling it yes. Similarly, this part I am calling it what?
Coordinate space distribution function.
Yes. Uh, okay, sorry. This is R. So did you know about it or any one of you? Was it done anywhere? I don't know, maybe in physics. It's fine. But did you notice one thing that these integrals are very easy to perform, no? Momentum. Why?
The square of momentum.
Because momentum is
Radial.
minus this kinetic energy is p square by twice m. No, this will be product of Gaussian integrals, isn't it? These are
Yes.
doable. If you integrate, you get this de Broglie's wavelength. You remember Thurman de Broglie's wavelength? You have dealt with, no? I'm just not writing it here.
Yes, sir.
So what is this phi? Then I can always write, okay, what is this phi? Phi is a function of to the power of n. In words, if I write, what should I write? This is the probability distribution of, for observing probability distribution for observing system at momentum space point. Similarly, what is R of this one? Same, no? Only in the, not in momentum space, but in configuration space or coordinate space, isn't it? Configuration space for any problem you ask me, huh? Okay, this is fine so far.
Yes, sir.
Not R, this is P. You should have told me, no? P. I hope I have not done anything wrong. Yes. This is fine. Whatever written, whatever I have written, should be fine. Now let me introduce this, what is known as reduced configuration distribution function. And just see my notation. I write capital P, 2 by n like this, r to the power of, sorry, r1 comma r2. What is this? This is joint probability distribution for finding particle 1 at r1 and particle 2 at r2. What should I write on the right hand side? What should I write? Any idea? Actually, what should I do? I should actually take this quantity, this p of r to the power of n. You
Integrate
understand?
all but those two coordinates.
Yeah. So it is actually, if you write explicitly, it is like p r1 comma r2 up to r to rn, no, for the nth particle. So what I should do here, I should actually integrate not only all the coordinates other than only r1 and r2, isn't it?
Yes, sir.
It's fine. But while doing so, I have another underlying assumption or understanding. What is that? Because I have understanding that the one I'm written here is actually a specific probability distribution. Why it is specific? Because it specifically requires particle 1 at r1, isn't it? And particle 2 at r2. You understand? The particle 1, I tag one of the particles as particle 1, another particle as particle 2. Now I have this condition specifically. What is the probability of finding a distribution where the particle 1 is at r1 and particle 2 is at r2? Then I should actually take this p to the power of sorry, not p to the power of p of r to the power of n, which is a function of n coordinates, and integrate over all the coordinates only other than r1 and r2. Is this clear? Clear to all of you? This is how it should be,
Yes, sir.
isn't it? But what the next question I can ask? What is the next question I can ask? Tell me. Any idea what next question I can ask? Next question I ask, okay, can I make it more generic? So let us do it. Now let us go to more generic. What do you mean by generic? More general, no? So Kailash, what should I
Any two
do?
particles that are at R1 and R2.
Yeah, so rather than saying particle 1 is at R1, 2 is at R2, I allow any particle, okay? I don't care which one. Any particle at R1, any particle at R2. So let us write down, and in this case, I'm using different notation. Rho 2 by n R1, comma R2. So in word, it is again joint probability distribution function for finding a particle now. This could be any one, no, any particle R1 and any other particle at position R2. Of course, you have in the n particle, capital N particle system. See my notation. Capital N means total number of particles. 2 means how many particles I'm considering. 2 particles. And these are having positions R1 and R2. But this could be any particle. But at R1 and R2. Then what should be the expression mathematically? Is rho 2 by n R1 comma R2. See how many ways I can choose the first particle. If you have n number of particles, capital N number of particles,
N ways.
n. How many ways I can choose the second particle?
N minus 1.
N minus 1.
N minus 1.
Yeah. So actually, I will have something like n into n minus 1, isn't it? And then I should have
Yes, sir.
rho, sorry, not rho, it's p, has to be p. Uh, Again, yeah. Fine? Is this fine?
Yes, sir.
Okay. So this is for two particle. So let us do it for more, even more generic. I calculate rho small n slash capital N. How many R's will be there? R1, R2, up to R small n, isn't it? I have say
Yes, sir.
5,000 particle, I choose 100 particles, like that. And what should I write rather than writing n into n minus 1? What should I write?
Factorial n factorial divided by small n factorial.
No, should be this. It should be n factorial divided by n minus small n factorial, isn't it? Manish, it has to be like this. Because you see, what is
Yes,
this?
sir.
This was nothing but n factorial divided by how many? N minus 2 factorial, wasn't it?
Yes,
This
sir.
is actually n into n minus 1. So in general, it is n factorial divided by n minus n factorial. And then I have what? I have the rest. And you remember the expression for this?
P small n by capital N.
Yeah, so
R1
let me
to R.
write down. Let me write down. It is actually dr to the power capital N minus small n. I'll tell you what is this. Exponential of minus beta u r to the power of n divided by what is this integral? Can anyone tell me my notation? This integral is,
Dr n plus 1 to dr capital N.
okay, this is the integral. Okay, is this clear? Is this clear? Because if you go
Yes,
and
sir.
see your definition, it is like that. And the quantity which is in the denominator, I am calling it capital Zn. And this is a name. This is called configurational integral. It is like a partition function. But the difference is that your integration is over the moment position, sorry, yes, position coordinates, so that you have potential energy there, not the whole Hamiltonian. Okay. What is the value of this configurational integral for ideal gas? Question. Somebody should answer. Kailash, what should be the value?
One.
If you cannot answer this, then I have a problem. Anish?
U potential is 0, right? Because there is no interaction
Yeah,
between
yeah,
the
yeah. So e to the power 0 is 1. But
unity.
then you have to
Because
integrate this. Yeah.
and then that becomes infinity if you take it over also.
No, no, not like that. No. Yeah, you have given volume. No? Your V is a
Oh,
volume.
yes.
Your number
Sorry.
of particles. So actually,
V star is.
each integral will give you V. If you cannot answer this, is a problem. No. So this is equal to the Zn is equal to V to the power of n for ideal gas, isn't it? Each integral give you V, and there are n such integrals, isn't it? Because what is going to happen? It is exponential of 0 is 1, and then you have dr1, dr2, like this, drn.
Yes, sir. Right.
and each of them will give me V. If you cannot answer, how can you do theoretical chemistry? It's difficult. Okay, so this is how it is. Okay, so this is configurational integral and it's fine. This is how it should look like because we're going to use this today's class. I hope that you're following.
Yes, sir.
So let me write down again. Uh, Let me write it down. Let me write it down. Yes. Your rho of small n divided by capital N is a function of how many coordinates? R1, comma R2 up to R to the power of n. Not R to Rn, isn't it? What is that? What do you have on your right hand side? You remember no? N factorial, n minus n factorial, n factorial divided by n minus n factorial. Okay, essentially,
Yes.
and this is z to the power of it's not zn, not z to the power of n. So I have 1 over zn, and then I have integral. What is the integral? Integral is something like dr. I'm writing explicitly. Okay. You understand now? If I write like this means you understand now? R to the power of n means actually this, all the n coordinates. Is this clear the way I have written?
Yes.
Essentially, this is what I did in the previous slide. Now, what I do, I just integrate this. I just integrate this. Integrate this. What do I do? I just take this. I integrate this over dr1 up to dr small n. What will happen to the left hand side? Sorry, right hand side? These are constant, no? What will happen here? Can anyone tell me what is going to happen? I'll have and what is this? Kailash, tell me what is this integral?
H power 3n by n factorial. Sorry, into n factorial.
This is actually Zn. This is Zn. Because we have all
Yes.
the I'm multiplying with dr to drn, integrate over all. So basically you have the whole integral here. No, this is Zn. This thing is Zn. Is this clear?
Yes, sir.
Or in other words, if I write in shorthand notation, rho n by n is a function of r to the power of n, which basically means all these coordinates. When you integrate over all the coordinates, this will give me because this zn and zn will cancel, isn't it?
Yes, sir.
Let me do it in a nicer way, isn't it? So this is one condition. It's a normalization condition. I can say this is like a normalization. So basically, if I write this rho 1 by n would depend on only one coordinate, no? R1 I can call it, doesn't matter which. What will be the right hand side? Tell me what is the right hand side of this quantity?
N into Yeah, just n.
N factorial divided by n minus 1 factorial, which is
Okay, so just n.
n. Because the number conservation, no, is it essentially?
Yes, sir.
Hope you're following. Not a very difficult thing so far. You can follow. So similarly, I can always calculate this rho 1 by n r, it depends on 1, r1. Explicitly, if I write down, what is going to be? N factorial, n minus 1 factorial, 1 by Zn. What will happen to this integral? This integral has everything other than r1, no? Sorry. Huh? Isn't it? If
Yes,
you have
sir.
any problem, tell me. Is this clear? Now, if you have for homogeneous liquid, when you are dealing with a liquid which is homogeneous, what is homogeneous liquid? Homogeneous liquid means that at some instant of time, if you have a particle sitting there at some position, if that particle goes, then immediately another particle comes within some time, within very short time, another particle comes and fill up that vacant position, isn't it? That is what is the meaning of homogeneous liquid. In solid, there are no exchange between the particles. The particles cannot exchange themselves because they are sitting on a crystal lattice. The particles are sitting on a lattice sides. They cannot exchange each other, isn't it? But for liquid, because of the diffusion, these particles can diffuse, can move. If one particle move from one side, then another particle can come from some other place and uh, actually fill that vacancy, isn't it? You understand? For homogeneous liquid, what does it mean? There will be no such defect, free of defect. The density is kind of uniform, isn't it? For homogeneous liquid,
Yes, sir.
there will be some local structure. There is a local structure in liquid, but for homogeneous liquid, what I can say, for example, this configurational integral, just look at it carefully. What is this configuration integral? It is, in general, is isn't it? But if I assume that my particle is fixed at r1, that is what is being done here, no? Here, any particle at r1, I'm telling, no? I'm assuming that there is any particle in r1. So if one particle goes, then immediately there will be another particle coming there and filling it up. Okay, so it's any particle at r1, what I'm talking about. So actually, what you can do, since you are tagging this particle, not the tagging the particle, tagging the position, what will happen to this? This integral will give you volume V. I can actually integrate this out, and this is actually going to be so it gives you a volume V times the rest of the integral. If it is so, then what will be the expression for rho 1 over n at, say, at calling it r1, let us call it r, because these are dummy variable. Look at it carefully. What is the n factorial by n minus 1 factorial is what? N
By
divided by Zn was there, and this one is what? This one is what? Zn divided by V, isn't it?
Yes, sir.
So this one gives you what?
N by V.
What is this? Density. No. So your one particle reduced distribution function for a homogeneous liquid is nothing but the density. Nothing but a density. So let us do something else. Let us do two particle. The two particle becomes difficult actually. Two particle is this 2 by n r1 comma r2. What will be there on the right hand side? N factorial divided by n minus 2 factorial 1 over Zn. Then what should I have? dr3, dr4 up to drn. So this is actually n into n minus 1. Sorry. N into n minus 1. Okay, fine. Now if you have ideal gas, what happens? Or any fluid actually. Ideal gas is a fluid, no? With no interparticle interaction, no? What will happen to this?
N minus 1 by V square.
Yes. So if you are in a situation where this will give me n into n minus 1, zn, sorry, not z to the power of n. And this is exponential of 0, which is 1. And then how many integrals are there?
N minus 2.
And each is of how much? It is v,
Yes.
no?
Yes,
N
sir.
minus
V
2.
bar N minus 2.
And what about this zn?
V bar N.
So what is going to be? What is the answer? Is the answer? Sorry, let me write down in proper way. So if you write down this way, this is divided by v square. Okay, and since n is very large, n is very large, n is very large, then what should I do?
N square by V square.
Basically, this will become equals to n square by v. Sorry, this will become equal. This is actually equal to n square by v square. Fine, fine. Is it fine? So it can be factorized two particle correlation. That's a two particle this distribution function into two one particle, because this is nothing but your when u 0, isn't it? This can be factorized, but in reality you cannot do for liquid, because why? But liquid is different from ideal gas, because these molecules or these atoms, the liquid is made of, they interact. There is an interaction potential. There is an interaction potential, that is u in my notation, and because of this interaction potential, you cannot factorize this rho 2 slash n into 2 to one particle distribution function. Is this clear? Then what can I do? So you can define things, and by defining things you can actually quantify the structure of liquid. So liquid has what is known as local structures. Locally there is a structure in liquid. If you go very far from a tagged particle, that structure is lost. You go to bulk, but locally there is a structure. For in case of solid, there is a global structure, isn't it? They are on lattice. So any integral multiple of this lattice spacing would find one particle in case of solid, isn't it? If you start from a tagged one, not the tagged one, the one which is sitting on a lattice side, and if you move in any direction uh, equal to this separation, you will find another particle sitting on the lattice side, isn't it? Not any direction, that particular direction, of course. Is this clear, Anish, Kailash, and others?
Yes, sir. Also, it is supposed to be fluid with no interparticle.
Yes. What you're saying? Tell me again. Tell me
On this,
again.
on the slide you were showing.
Yes. Okay. No, I'm saying this is for no interaction, but now I'll go with interaction. This is for ideal gas, this part. Okay. So now if you go to real liquid, how to quantify this? In order to quantify this, let us define something. What can I define? Let us define something like G R1, R2. Define in such a way that this is actually rho 2 by n. So what is the value of this quantity? This for ideal gas, what is the value? Can anyone tell me?
Unity.
It will be rho square by rho square ideal gas, no?
Yes, sir.
Ideal gas. So basically, if I go to a very large separation, I have a tag particle and I go very, very, very far, that particle would not know this tag particle, so they will not interact, no? In that case, I should get my ideal gas distribution, isn't it? It should be 1.
Yes, sir.
Okay, now this is another, also you can define, we can define something else. This is called HR1 R2. This is rho 2 by n R1 comma R2 minus rho square. This is nothing but your, isn't it? This is like this. This
Yes, sir.
G is called, G as well as G is called, there's a name to this, is called pair correlation function. Also known as radial distribution function for liquids or for fluids. It's called pair correlation function or radial distribution function. Okay. Now, if I put one of my particles at the origin and then I write this P2 by n, first particle is at the origin, another is at a position R, radial position R. This is going to be what? Rho square G of R. Okay, G of R. Is this clear? It has to be rho square G of R. Similarly, and if I write like this, P2 by N 0 comma R divided by rho, this will give me rho times G of R. And what is this? This is actually conditional probability that a particle will be found at R given that another is at the origin. Okay, so rho times G of R. So let's look at it. This 2-point distribution function divided by the density, the bulk density. Rho is called the bulk density. Of the fluid. So this will approach what? What will be the value of this? Can anyone tell me? Rho 2 by N by rho when R is very large. What do you expect? Let's look at this expression.
Rho.
Because you know G of R becomes 1. So it will be rho. Because that is what you should get, no? Because
Yes,
that should
sir.
match with your bulk density. This is exactly what you're getting. So you can also interpret this in some other way. You can also say this is nothing but your average density of particles at R, given that a tagged particle is so I can say whenever I talk about liquid structure, it is equivalent of saying what is G of R. Look at carefully, very carefully this expression. What you can see here that if G of R is 1, then this average density matches with that of bulk density, isn't it? Any deviation from the bulk density is given by G of R. So that's why G of R talks about local structure in a liquid or in a fluid. Is this clear? If G of R is 1, then your bulk density and your 2-point reduced density, they match. Okay? Is this clear that they're matching?
Yes, sir.
Okay. So they are matching. But if you are not, if your R is not very large, then there will be some local structure in liquid. And what will happen to that? That is taken care of by this G of R, which is a radial function of this radial distance R. That's why it's called radial distribution function. So let us look at it carefully. Can you see this? So this is a typical snapshot of liquid. Can you see the picture, all of you?
Yes, sir.
So the one here, this is my tag particle, okay, and I assume this is my origin. My origin is the tag particle. I fix my origin at the tag particle, the one in at the center, okay. And if I move radially outward from that tag particle in any direction, I will see there is a change in density. No, if I go to very long distance, it will match the bulk density. What is the bulk density? You have G of R. It would be something like 1. Remember, the G of R is 1 when R is large. So you can see this is the plot of G of R for, I think it's for argon, liquid argon and gaseous argon. You can see the liquid argon, there is a peak at sigma. What is this sigma? So each particle, these are argon atoms, they are of van der Waals radii, they have the van der Waals radius sigma. So if I move from here to here, I'll find what is known as fast coordination shell or solvation shell. In this case, coordination shell I'm calling it. What is the distance between this center and this center? Can anyone tell me? Rough distance. If the two particles are almost touching, what is the rough distance between this center and this center? In terms of sigma, can anyone tell me? Sigma is the diameter of the particle. Two particles almost
Sigma.
touching. It will be around sigma, isn't it? Half sigma by 2 plus sigma by 2. Maybe slightly,
Approximately.
yeah. But so that's why you should see a fast peak at sigma. Can you see a fast peak at sigma? G of r.
Yes, sir.
And then it goes down. Why? And you can see that G of r is very low when you are between sigma and 2 sigma. Why? Because the next peak appears at 2 sigma, no? Second coordination shell, sigma plus sigma. But between sigma plus sigma 2 sigma, probably this G of r is not 0, but it is quite low. Why low? Because that local structure tells you that you should have peak at sigma and 2 sigma, because there is a local structure. So having peak at sigma and 2 sigma and having a low value of GR in between actually tells you there is a local structure in liquid. There is something called local structural order in liquid. Is clear? There is a local structural order in liquid. What about gas? You can see there's a peak maybe around sigma, but then every gas, in case of gas, these particles diffuse and their interparticle separation is quite large. They are moving very fast, they are diffusing. So no such local structure. Is this clear? Sigma to sigma, then eventually in the long distance, long separation, it will match with GR equals to 1, the ideal gas value. Is this clear? So from 0 to, this is something like first solvation shell, this is like second solvation shell or coordination shell. Is this clear? This has been talked many times in many other contexts in chemistry. Any question so far? Then I'll ask a question. Let me have some water. Any question, please? Okay, let me ask a question. Hope you guys are there. I don't know whether you are there. Hope so.
Yes.
Okay, my question is as follows. If it is the case, then tell me what will be the structure of a crystalline solid. And we will stop here because I have something to do. Today I'll skip now. But tell me what will be the structure of solid.
Similar to what we have for liquid.
Then how can you differentiate between solid and liquid?
The peaks will be sharper, I guess, and
Yes.
more spaced out, depending on the lattice parameters.
So this is from the book by David Chandler, I think Introduction to Statistical Mechanics, the name of the book. It's a fantastic book. It's chapter number 7. You can see the book. It's the book. Okay. For solid, I told you that they're on the lattice and they're vibrating on that lattice side, isn't it? They cannot diffuse much. So I'll have sharper peak at sigma, whatever the value. And what will happen? There will be no diffusion in solid most of the times. So as a result, my G of r between sigma and 2 sigma will go to very, very low value. It will go to 0. So probability of finding a particle between sigma and 2 sigma will be extremely low for solid. But there is a finite probability of finding the particle in terms of liquid, because liquid diffuse much more, liquid particles. Is this clear? Is this
So
clear?
this means that if we see deviation in G of R between sigma and 2 sigma and solid, that could be a signature of defects in packing.
Yes. So a typical solid would look like this. Can you see the G of r drops to 0 between sigma and 2 sigma? And they're peaked at sigma, very sharp peak at sigma, root over 2 sigma, root over 3 sigma. In this case, depending on the lattice geometry, of course. You understand?
Yes, sir.
And actually, if you integrate this g of r from 0 to say in some value, what are you going to get? You're going to get coordination number, which we'll talk about in the next class. So actually, you go from 0 to some r cut, then what you get is called the coordination number. Okay, so we'll stop here today because I have some other thing to do today, and this is quite heavy because the one I showed you. Please try to read
It's
David Chandler.
root
Yes,
2 over sigma in
that
this case of solid in the diagram.
yes. What is the question?
Why is it root 2 sigma in?
Oh, this is because you just go to any I don't know which geometry you're talking about, depending on the geometry of the lattice, isn't it? What kind of unit cell you're talking about? You understand, no? If you go to different unit cell, it is not there's a cubic lattice or any other lattice.
Yeah,
Depending on
yeah,
that,
yeah, yeah.
it
I
will change.
understand.
It may not be sigma. It will be
Yes.
some in orders of sigma, but not exactly sigma. Okay, we'll stop here today, and next day I'll do a little bit of this, and then I have to talk about MD simulation. Maybe next day, if not next day, the next to next day. Okay, so I'll send this slide today, and take care. We will be
Thank
meeting on Thursday. Yeah, thank you.
Thank you, sir.
Thank you, sir.